Hi there, and welcome to this video on the topic of lenses. What do glasses, telescopes, and microscopes have in common? They all use lenses to allow us to see more clearly, see things which are far away, or see things which are very small. There are two basic types of lenses: convex or converging lenses, and concave or diverging lenses. We'll be looking at how both types of lens work in detail over the rest of this video. Lenses are normally made from glass, but can be made from plastic or any transparent material. What will happen when this light ray, which is travelling in air, strikes this convex lens which is made from glass at this point? Because the ray is travelling from air into glass at an angle to the normal, it'll refract towards the normal. When it reaches the rear surface of the lens, because it's travelling from glass back into air, it'll refract away from the normal and will carry on travelling through the air in this direction. This ray was initially travelling parallel to the principal axis of the lens, an imaginary line which cuts through its centre like this. If we direct 4 more parallel rays of light towards the lens, they'll follow these paths. Notice that, because the middle ray is travelling along the normal, or is striking the lens at an angle of incidence of 0 degrees, it doesn't refract as it enters or exits the lens. Something interesting has happened to the right of the lens here. All 5 rays of light have ended up travelling through the same point. This point is called the principal focus of the lens and is often represented in ray diagrams by a capital F. The principal focus of a convex or converging lens is the point through which light rays which are initially travelling parallel to the principal axis will travel after being refracted by the lens. The distance between the principal focus and the lens is called the focal length of the lens. A convex lens can be used to form an image of an object on a screen, such as a piece of paper or card. This type of image is called a real image. A real image is formed when light rays converge to a point, and so can be projected onto a screen. We can use a ray diagram to determine what the image of an object which is formed by a convex lens will look like. This is the symbol for a convex or converging lens which is used in ray diagrams. Here, we've placed an object which is represented by this arrow beyond 2f, or twice the distance from the lens to the principal focus from the lens. Notice that the bottom of the object is sitting on the principal axis, which means that the corresponding part of the image will also be on the principal axis. By drawing 2 or more light rays from the top of the arrow which represents our object, we'll be able to work out where the other end of the image will be, which will give us the size and location of the image. It's essential that you learn how to draw each of these light rays from the object, as this is something which you could be asked to do in your exam. Using a ruler, you should draw ray 1 parallel to the principal axis like this. When it hits the lens, it'll be refracted and it will then pass through the principal focus like this. If you've really been paying attention, you might have spotted that this ray should actually have been refracted twice as it passed through the lens, once on its way in and a second time on its way out. We can ignore this effect if the lens is thin, however, and in any ray diagrams you'll be asked to draw, you'll just have to remember that any rays which are travelling parallel to the principal axis should go on to pass through the principal focus upon exiting the lens. Moving on, ray 2 is easier to draw. It just goes from the top of the object arrow through the centre of the lens without changing in direction like this. Finally, ray 3 first goes through the focus which is on the same side of the lens as the object. When it hits the lens, it then travels parallel to the principal axis like so. The point where these 3 rays meet marks the location of the point in the image which corresponds to the tip of the object arrow, which means that our entire image looks like this. In this case, with the object beyond 2f, the image formed is real, inverted, and diminished. To recap, a real image is an image which is formed when light rays converge to a point, as has happened here. A real image can be projected onto a screen, so if we placed a piece of card, paper, or another screen here, we'd be able to see an image of the object. By inverted here, we mean that the image has been flipped both vertically and horizontally, although we can only see that it's been turned upside down in this 2-dimensional ray diagram. Finally, when we say that the image is diminished, we mean that it's smaller in size than the actual object. In this example, we're going to find out what happens to the image when the object is moved a little closer to the convex lens, in this case between f and 2f as shown. Even though we drew 3 light rays just a moment ago to determine the location and size of the image, we can actually get away with drawing just 2. So from now on, to make our lives a little easier, we're going to draw just rays 1 and 2 in our ray diagrams. Starting off, ray 1 goes from the tip of the object arrow parallel to the principal axis and towards the lens like this. When it gets there, it's refracted, and then it travels down through the principal focus on the far side of the lens like so. Ray 2 starts again from the tip of the object arrow and goes straight through the centre of the lens, something like this. That means that the image of the object must be located where these 2 rays cross, which is about here. For part B, we can see that the image has again been formed by real light rays which have converged or come together, that it's upside down as compared to the object, and finally that this time the image appears to be bigger than the object, so we describe the image as being real, inverted and magnified. As we've just seen, the image of an object which is produced by a lens can be either magnified or diminished, or bigger or smaller than the actual object. The equation for the magnification produced by a lens looks like this. Magnification equals image height divided by object height. Both the image and object heights will have units of distance, so millimeters, centimeters or meters. The most important thing to remember in calculations here is that both heights should have the same unit. You shouldn't mix meters with centimeters, for example. Because the magnification is just a ratio of distances, it doesn't have a unit. If the magnification is greater than 1, it means that the image is bigger than the object, and if the magnification is less than 1, it means that the image is smaller than the object, in other words that the image is diminished. Have a look through this example now. Hopefully you'll see here that the film, which is the object, is being projected onto the screen, which is where the image will be formed. Using our equation then, and keeping the distances in meters, on the top line we have 17.5, and on the bottom line 0.035, which is just 35 millimeters in meters, which gives an answer of 500. Remember that to convert 35 millimeters to meters, we just divide 35 by 1000 because there are 1000 millimeters in a meter, which is where we got our 0.035 from. The last thing we're going to look at for convex lenses is what happens when the object is placed between the lens and its principal focus like this. Let's draw rays 1 and 2 as we did before. Ray 1 travels parallel to the principal axis, then through the principal focus on the far side of the lens like this, and ray 2 goes straight through the centre. This time, something strange has happened. As the rays travel to the right, they're actually getting further apart. Does this mean that no image is formed here? Well, not exactly, because this is how a convex lens is used as a magnifying glass. If we look towards the lens from this position, it seems to us as though both rays from the tip of the object arrow originated from this point. This marks the location of the virtual image of the object. From our work in reflection, we know that a virtual image is an image which is formed by light rays which appear to diverge from a point, and that a virtual image can't be projected onto a screen. We can see also from a ray diagram that the image formed is upright, meaning the same way up as the object, and magnified. Before moving on, you might like to pause the video at this point to make sure that you've completely understood the 3 different types of ray diagrams which we've gone through for convex lenses. Concave or diverging lenses look like this. They are thicker at the edges and thinner in the middle. Following the usual rules for refraction, this light ray, which is initially travelling parallel to the principal axis of the lens, will refract towards the normal on entering the lens and away from the normal on leaving it. If we apply the same rules for these 4 other rays, we find that the lens has this effect on the light that enters it. It causes initially parallel rays of light to diverge or spread out. If we extend the 5 rays which emerged from the lens to the left, like this, we find that they meet at this point, which marks the principal focus of the lens on this side. This is the point from which the refracted rays appear to diverge. As before, the focal length of the lens is the distance between its centre and the principal focus. No matter where the object is placed, the image formed by a concave lens is always virtual, upright and diminished. Let's use a ray diagram to explain why. Ray 1, as always, starts by travelling parallel to the principal axis. When it strikes the lens though, Because this is a concave or diverging lens, something different happens. To work out the path of this ray to the right of the lens, we have to draw in a dotted ray between the principal focus, which is on the same side of the lens as the object, and the point at which the ray strikes the lens, like this. If we then extend this line to the other side of the lens, it'll mark the path of ray 1 after it exits the lens. Ray 2, as always, goes straight through the centre of the lens. The point at which these two rays cross shows us the location of the virtual image, which we'll be able to view from this direction. Remember that it's virtual because the light rays which form this image only appear to diverge from this point. If you placed a screen at the location of the virtual image, no actual image would be projected onto it. One last example now to see you on your way. Why don't you pause the video before seeing how it's done? As you can see, in part A, we're looking for the location of the virtual image formed, so let's give it a go. Ray 1 first starts from the tip of the object arrow, then goes straight towards the lens parallel to the principal axis like this. We then draw our dotted line from the principal focus up to the point at which ray 1 strikes the lens like this, and then we continue this line to show the path which ray 1 follows after it leaves the lens. Ray 2, as always, goes straight through the centre of the lens like this. That means that the image is located here, virtual, upright and diminished as expected. For part B, because each of the big squares represents 1 centimetre on the scale, that means that our image height must be about 1.2 centimetres. Lastly, for part C, using our magnification equation and subbing in, we have 1.2 divided by 3, which gives an answer of 0.4. It's a magnification of less than 1 because the image is diminished. That brings us to the end of this video. Now that I've gone to such great lengths to help you with your lenses, the least you could do would be to try some of the exam style questions. Enjoy!